First, I would like to welcome everyone to the technical launch of the Open Simulation platform. My name is Lars. I'm a senior researcher at SINTEF, and I'm one of the many people involved in the development of the Open Simulation platform, or OSP for short. We have several speakers here today to talk about various aspects of the OSP. I'll let them introduce themselves and I'll soon give the word to them. But first, I will give you some brief information about this event. First of all, I need to inform you that this webinar will be recorded so we can make the presentations available to others afterwards. Only the panelists, the speakers, will be recorded, of course. However, you in the audience will be able to post questions using the Q&A feature that you find in your Zoom client. And some of those questions may be read aloud and answered live by the panelists. So if you have a problem with your question being recorded, please don't ask it. Otherwise, feel free to use the Q&A feature to ask questions if there is anything in the presentations that is unclear. And we in the OSP team will try our best to answer as many questions as we can. And please use the Q&A feature and not the chat, because then it's a lot easier to link the answers with the questions. Some of you will have the opportunity to ask more questions and possibly more advanced and/or comprehensive questions in part 3 of the workshop. I'll get back to that shortly. We're calling this event the technical launch because it's aimed at researchers, engineers, and students. Some of you may have attended the official launch last month and will therefore already have seen some of the things we present before. However, here we will go more into the technical details. There will be live demos and there will be code, just so you're warned about that. The webinar you're attending now is part 1 of the launch event, and it will last until 11:30. We'll have a short 5 to 10 minute break in the middle of it, sometime between 10 and 10:30, depending on when the various talks end. So people have an opportunity to stretch their legs, catch some air, or do whatever you need to do in the middle. And as I said, part 1 will be complete at 11:30. Now, some of you have also signed up for parts 2 and 3 after lunch. Part 2 starts at 12:30, so there's a 1 hour lunch break between parts 1 and 2, while part 3 starts at 2 o'clock or 14 o'clock. Those of you who were able to secure seats there have received separate links for each of them. The link you used to sign into this webinar will not work. With all that said, I hope you enjoy this workshop. And with that, I give the word to our first speaker, Kristine Bruun Ludvigsen from DNVGL, who will give you an introduction to the OSP.
Try again. Hi. Thank you for the introduction, Lars. I see in the chat that some has a problem with the sound. I could hear Lars perfectly, so it might be not on our side, but on the other side. So, but apart from that, my name is Kristine Bruun Ludvigsen, as you see, and I work in DNVGL in the Maritime Advisory Department. And I will introduce the Open Simulation platform today, if I can find the right slideshow and share with you. Here. Yes. I hope you can all see it now. Let's see if I can. Yep, now I assume that you see my, yeah, now I can see where it is. Sorry for a slow start here, but what I will do today is to give you a short introduction on why and for who we initiated this Open Simulation platform project around 3 years ago, I think it was, and also introduce some of the concepts or principles we see as key in order to develop a business ecosystem, as we call it, for sharing maritime simulation models. Yeah. The OSP initiative was started as an answer to the increasing challenges our industry has with complex systems. As over the past decades, ship systems have become increasingly complex, software-driven, and integrated. And for a ship, these systems and equipment are normally delivered from a range of different manufacturers, meaning that the system simulations will be important, meeting increasing challenges our industry has with, for instance, assuring optimal designs, in assessing whether the system is safe and fit for purpose, and in commissioning and integrating systems and software on board vessels. When planning complex operation and proper human-machine interactions, when performing change management, both during construction and in operation. And simulation doesn't directly address the cybersecurity, but may facilitate the increasing need to update and patch systems on board. So, looking, for instance, at the typical timeline for traditional ship design today, we know that integration tests are typically conducted towards the end of the construction phase, and that gives us minimal room for changes in the design. So, with the open simulation platform, we are trying to enable the industry to shift left, or what we mean by that is to move the commissioning and integration to earlier in the timeline through establishing simulation models of equipment and systems early in the design phase. So what we then do is to facilitate virtual system integration, commissioning and testing before the physical vessel is built. And through this, we mean you can save time and reduce the risk both during commissioning and during sea trials. And the same systems digital twin, when you know how to spend resources in establishing this, it can follow the real twin into operation and enable a range of use cases supporting the operation of the real asset. For instance, change management, as we mentioned, and crew training, operational planning. The digital twin concept is maybe commonly thought of as a 3D visualization of the asset. But a digital twin that mirrors the physical asset can be composed of a range of virtual information. And in OSP context, we focus on the computational models and algorithms that together with the software can replicate the dynamic behavior of an asset. So to explain a little bit more what we mean about this digital twin component for system simulations, here's a sketch of a component or a system including the physical equipment on the right and the control system on the left, and as it works and interacts in real life during operation. In a virtual representation of the system, all hardware is represented by models, taking it one step further than, for instance, traditional HIL testing, where you also keep some of the hardware in the loop. So here you see that on the right side, both your dynamic system is modeled, the actuator, the sensors are modeled. And the control system software shall then not notice the difference between being connected to the real equipment and the simulated equipment. And since this complete setup now consists only of software, it can be viewed as a digital twin component containing both the physical models and the equipment and the control system running on it. So the simulation can in principle run anywhere with sufficient computing power, be on your regular PC, on a local server park, or in the cloud, as I try to illustrate here. But some additional advantages of this is that when you have everything virtual, you can potentially accelerate the simulations in time. And you can test much faster if you're able to control the speed both of your software and models. And simulations can also be parallelized in a more efficient way and increase further the test efficiency of such systems. And also during design, it could be important to be able to run a lot of scenarios efficiently with your simulation models. And just to add on, for some components, one may not have the need for the actual control software, as you see here in the model, but it might, for instance, in the design, it might not be ready yet. So the control system may also be represented by a model, and then we can call this representation maybe a model in the loop. But based on this concept of the digital twin components, the figure here shows the main component or concept of the open simulation platform. The idea is to adapt and develop standardized algorithms and so that we are able to interface these digital twin components for different manufacturers or other providers to be connected into one common simulation. Above the gray line here, you see the different equipment represented by digital twin components that we saw earlier. But we can also imagine that you can connect the control systems directly to the simulation, or that it could be simulation models not containing control system, for instance, pure hull models or environmental loads. And finally, we see the need for a remote interface enabling distributed execution of models. And that is that some models or this setup requires that everything is on the same server as illustrated here, but some models will be need to remotely interface, for instance, because it needs to be run on a dedicated computer or dedicated server. So that's why these algorithms that we developed allow for also remote interface. So what's next? Yeah, who would benefit from access to the open simulation platform? What was the idea? And the idea is to justify the development of these system simulation models. We must make the most out of the system model, and it should therefore be accessible for a range of users. And throughout the project, we have identified potential benefits for example, owners, component suppliers, designers, crew, operator, service providers, and class. And they can all expand or improve their product, tools, services, and operation through increased use of simulation tools, as we try to prove. So, the Open Simulation Platform is a joint effort initiated in 2017 by the 4 partners, Kongsberg Maritime, NTNU, SINTEF, and DNVGL. And we were encouraged to establish a joint industry project quite early in this initiative to confirm that the ideas behind the Open Simulation Platform was supported by the industry. And the list of partners that joined us shows the support from a wide range of stakeholders. And the main development you see today has been conducted by the 4 initiating partners, and there's also us presenting here today, but with very valuable input from the JIP in the workshops and the use cases in particular. So here's a screenshot of our webpage, where all results from the JIP is shared. It was concluded in June this year, and you will also find more on the background that I've just briefly introduced now. And what you can find is the co-simulation software and interface specification that Levi will demonstrate later today. You will find the interface specification will be presented by Håvard, sorry, and the co-simulation software by Levi. The reference models will also be found. We have a set of reference models and configurations. And one of these configurations will be used for the exercises this afternoon. And we will also share experience from the use cases. And so it will all be briefly introduced today, but you can look at it more in detail and also download it from the project webpage. And next, I will briefly introduce some of the key concepts we are using in the OSP project. So to summarize, the vision of the OSP project is to enable collaborative digital twin simulations to solve challenges within design, commissioning, operating, and assuring complex integrated systems. And typically what we mean by these systems is where you have multiple suppliers delivering components, sensors, and software that should be able to operate together. And for these systems, it's where we consider simulation models on the open simulation platform important. So to enable this vision, the OSP was founded on a set of key properties. I will quickly introduce them now and go slightly more in detail on some of them in the next slides. First of all, in the upper right corner here, simulation models are used for a range of applications today. And OSP must enable model reuse to achieve the scale and efficiency of building digital twin simulators. Protection of IPR is essential in order to actually be willing to share and reuse models. And this requires black boxing of the individual simulation models and also making sure that they cannot easily be reverse engineered. So a major challenge then is to enable the integration of these black box models originating from then different stakeholders, simulation tools and platforms in one system setup. And we see co-simulations as a method to solve this. Interoperability and common standards are needed to enable efficient construction of large co-simulations from individual components. And our goal is to build on established standards whenever possible, and only adapting and expanding on this when we see the need to develop something which is beneficial from our maritime context. In order to drive standardization, ensure interoperability between stakeholders and tools, and enable common working processes, we believe that a common open source software co-simulation is needed. And to conclude, the challenge of complex systems is too big to be taken on by any individual stakeholder or tool. So therefore, OSP strongly focus on collaboration and interoperability. And that's why we reach out to you, for instance, today as a future user. To start with the basic, we know that simulation is a core enabling technology when designing, optimizing, and operating all new assets almost today. And specialized tools and knowledge for modeling are created in all different fields, but they are typically not made available for collaboration and reuse. And to best make use of these investments and assets, we need a unifying approach to enable digital collaboration across many disciplines and sectors. So one such approach is co-simulation. And it allows to couple independent standalone simulation models, each of those including solvers, to establish full system simulations. And co-simulation is well suited when the sub-simulations span a range of physical and engineering domains. So, for instance, if you are developing your tools in MATLAB or in Simulation X, you can combine them. You don't need to convert them, but you can just package them and combine them in a co-simulation. And that is why co-simulation is the approach we have taken in moving towards this OSP vision. And we want to make use of the simulation models already developed. So for this, we have adapted the use of the functional markup interface as a standard for co-simulation. And I assume that many of you are already familiar with it, and you can find the details on easily online. But it is a tool-independent standard for making submodels compatible with each other in a co-simulation context. It is completely open and free to use, and is supported by a large and growing number of tools. And it's also inspired by that we are want to make the open simulation platform open to accelerate development. So say that you have a model in your simulation tool, and this tool has FMI support. Then you can export it as a functional mockup unit and for use in, together with others. So we illustrated in back here, and that's because in the process of exporting the simulation model, it is compiled to binary code and therefore appears to all users that you share with them with as a black box model. And by using the existing FMI standard, we kind of come a long way towards achieving model reuse and IP protection for in our system. But we also want to add on this. So what is the special with OSP Co-simulation? And this slide illustrates 3 partners that want to collaborate on simulations. And FMI provides compatibility at a low level because they all make models as FMUs. But it doesn't provide higher level information about what the simulation variables mean and how to set up the model interconnections. So coupling the models to create a co-simulation setup could be a challenging task. In the lack of a common language with respect to variable naming and semantics, we have developed the OSP Interface Specification that Håvard and Martin will introduce next to efficiently create co-simulation setups. So with OSP-IS, we then build on FMI and a layer of, we build on top of FMI a layer of semantic meaning to the simulation variables that makes them easier to connect. And now we have a set of models coupled and configured ready for simulation. And the obvious missing piece in the picture is then the co-simulation software that we have also developed. It orchestrates the co-simulation, meaning that it handles time synchronization between each of these FMUs. You remember have their own solvers, but the co-simulation software is then the part that orchestrates the communication between the models. And in addition to driving the simulation, the OSP software includes several important features and a set of applications that Levi will demonstrate later today, which makes it possible for to build on top of these basic building blocks and make useful tools for your design and operations. So I was quite quickly going through this, I see, but some concluding remarks to say that although the JIP is concluded, OSP development has not stopped. Our goal is that the open source software specification and example configurations from the JIP will form the basis of an open source community around the OSP project. And what we mean about that is that we want the industry to use the code that we share in internal development and also in collaboration with the academia in R&D project that will benefit from the OSP software as a tool and then contribute back to a joint development. Because that's what the OSP or the Open Simulation Platform is meant to be. It's a tool to facilitate all these, all the potential services and applications that you build on top to improve the way that we handle our complex systems today. And in parallel, we in DNVGL are developing platform services that with the main goal of these platform services is to manage secure sharing of models, to perform assurance of simulation models, and to make available an infrastructure to perform efficient simulation models on a neutral ground for collaborations. And thus we have our own commercial interests in the success of the Open Simulation Platform, and we believe that it's important that many stakeholders have a commercial interest in this to drive the work forward. And the way we want to drive this forward is, of course, through the commercial and pilots and projects, but also through R&D projects together with the industry and with academia. And we are also happy to see that we are not the only ones adapting this. Of course, our core partners are doing it, and suppliers, we see the increased interest from suppliers and equipment manufacturers in developing their own infrastructure to accommodate for sharing simulation and to make interface between simulation models, between software, increasingly standardized. And we continue from the OSP project to encourage interoperability between platforms and services. And the main goal is to assure the freedom to choose technology and a collaboration form that suits your company or your project going forward. So, and of course, when doing this, we will have a feedback to the open source project, and that is important. So I was jumping quite fast through this, but as I said earlier, most of the background information, a lot of high-level explanation of why we are performing the Open Simulation Platform project is available on our website. And to introduce or to tell you more about the OSP Interface Specification, I now give the word to Håvard Nordahl, there you are, and who comes from SINTEF Ocean, and he will present the interface specification for you. Thank you. I guess I have to stop sharing. There you are, I think.
Yes. Okay, then hopefully you see my screen. So my name is Håvard Nordahl, and I'm a researcher at SINTEF Ocean. And I will now give you an introduction to the Open Simulation Platform Interface Specification, or OSP-IS. And as we heard from Kristine earlier, Co-simulation is a great tool for building system simulations from independent sub-simulators. And FMI gives us a standard for exchanging and running these sub-simulators and ensures binary compatibility when we connect the FMUs through the FMU variables. However, FMI lacks a shared language with rules and definitions for these variables. The FMU developer is free to name each variable as he or she wants, and the same is true for unit representation. This means that the person connecting to FMUs must consult the FMU documentation and interpret variable names to deduct the semantic meaning of each variable. This is difficult, error-prone, and time-consuming. Just look at this simple example. It shouldn't be hard to connect a mass, spring, and damper, should it? But still, as we see here, it can easily become quite a difficult task, where it is easy to make mistakes and spend a lot of time. That is why we need to make model connections easier, safer, and faster. So what would be an easy way to connect to FMUs? I would say that it would be very nice and easy if we could simply say that FMU A is connected to FMU B and don't have to worry about how all the FMU variable connections are made. Making connections in this way implies that we want the computer to do most of the connection work for us. We want it to automatically connect each variable when we tell it that FMU A and B are connected. To make something like that possible, we need a way of expressing the semantic meaning of each variable, how variables are related, and define rules for connections of variables. And it has to be done in a machine-readable way. We also need automatic validation of connections. And all in all, that is why we chose to build the interface specification on an ontology and connect definitions in the ontology to the FMU variables. So how is the ontology organized? I'll go through this now while comparing to FMI to show what our ontology offers in addition to what you get from FMI. So let's start by looking at the variable. It has a data type, causality, and unit. Data type and causality is defined by FMI, so these can be retrieved from the FMU. Units are also defined, but in FMI 1.0, it is simply an unrestricted string, whereas in FMI 2.0, the units are defined in terms of combinations of SI units. We have adopted the unit definitions from FMI 2.0, enabling FMUs on version 1.0 to define units in the same way. And additionally, we have extended the definition with percentage as a base unit, since it is widely used in the industry. So our variable definition is quite similar to that of FMI. And a given variable can be represented like this. And here, my variable is a variable, is of type real, has unit meter per second, and has causality input. But we need more semantic information to achieve our goal of simple FMU connections. So the next step we took was to make it possible to define logical groups of variables and to assign a type to the variable groups. The ontology therefore contains the concept variable group and concepts for various variable group types. Each variable group type has a set of defined restrictions on number of variables, causality of variables, and units of variables. As an example, a variable group can be of type force, and all variables in a force type variable group must have the same data type, units, and causality. So now we have seen how we can group variables into typed groups with rules for their contained variables. And we have exploited this to add the connection rules in the ontology, such as a variable group of type force can only be connected to a variable group of type force where the variables have opposite causality and matching units. This makes it possible to connect a force variable group output from FMU A to the force variable group input of FMU B, as seen here, without having to worry about the connections of each individual variable. And then, to make connections even easier, we have taken inspiration from bond graph theory and defined a variable group type called port. A port is a subconcept of a variable group with additional restrictions stating that it must consist of exactly two variable groups, where one variable group only has input variables and the other only has output variables. Using the port concept, we can model bonds from bond graph theory, which is a favorable framework when connecting physical quantities between simulation models. And we can model pseudobonds. This allows us to connect the FMUs on a higher level. In this example, the linear mechanical port of FMU A can be connected to the linear mechanical port of FMU C, while it cannot be connected to the electric ports of FMU B and C. So how do you add the semantic information to your FMU? Well, our solution is to add an XML file called OSP Model Description XML to the FMU, where links between the FMU variables and the ontology are defined. You might ask, doesn't that mean more work? I mean, since we have to make another file? The answer is that overall, this will reduce the workload significantly because the OSP Model Description XML file is made only once by the model developer, while every user of the FMU no longer needs to spend time figuring out meaning of variables and how they should be connected. Now that you have your FMUs with the OSP Model Description XML files, you can connect the FMUs through variable groups by using our file format for connections, OSP System Structure XML. Martin, in the next presentation, will come back to the details of both OSP Model Description XML and the OSP System Structure XML. When you have used OSP-IS to enrich your FMU variables with the semantic information, you can use a validator to verify that your OSP Model Description XML and the OSP System Structure XML are compliant to OSP-IS. We have also defined the error classes in the ontology such that clear and meaningful error messages can be provided. And this is because standard reasoners, which are used to validate an ontology, gives quite obscure error messages. In addition to validating your configuration, you can use the validator to build the functionality for automatic connections by using it in a tool to block illegal connections and to allow legal connections. And this would make the construction of system simulations from FMUs easy, safe, and fast. Some challenges still lie ahead, and this will not be solved only through updates of OSP-IS. However, OSP-IS will play an important role in the solution of each of these issues. First, we have proposed a solution for interfacing simulators to hardware, such as dynamic positioning controllers. However, we need more practical experience to evaluate and improve this solution before we can say that OSP-IS covers and simplifies a vast variety of information flow interfaces. FMU variables may be represented in different coordinate systems, and we want OSP-IS to facilitate automatic conversions. And we have investigated this problem and have some ideas that we need to investigate further and test out. Some equipment may be tightly coupled in the physical sense, like a hull and a crane. So even though it makes sense to let the crane specialist develop a crane FMU and a hydrodynamic specialist develop a hull FMU, splitting such systems into co-simulation FMUs results in stability issues. So we are therefore looking into alternative ways of handling such issues. And currently, there's no standard for exchanging a parameterized environment, and interactions through a shared environment is also needed in some applications. So this is also something we're looking into. So how can you contribute to the further development of OSP-IS? Well, every time you encounter a situation where the definitions in OSP-IS does not support your case, let us know. You can send any suggestions to contribute-ospis@opensimulationplatform.com. And if you have specific variable group suggestions, you can go to Appendix B in the OSP-IS document, copy the form, fill it out and send it to us. Appendix B also contains some pre-filled example forms to guide you in how you can use this form. And if you would like to include some explanation in addition to this form, just write the explanations in an email and attach the form. Then next up is Martin Rindarøy from SINTEF, who will take us through the steps of making FMUs and show us how we can use OSP-IS to get from this rather frustrating situation to a much simpler and nicer situation where connecting FMUs is easy, safe, and fast.
Yeah, thank you, Håvard. Let me try and share my screen here.
Yeah. Need to.
There we go. Yeah, So my name is Martin Rindarøy. I'm a researcher at SINTEF Ocean. I'm first going to quickly introduce FMI, how the bits and bytes that make up an FMU, how you can make one manually by hand, and I'll show a simple example of how a tool like OpenModelica supports FMU export, and what the generated FMU from a tool like that looks like. Then I will go on and demonstrate how to make OSP model description XML files and OSP system structure XML files. And finally, I will run some examples using the command line interface tool with the OSP validator to validate some OSP system structure XML files and some valid ones and a couple of examples with some validation errors. So first, FMI consists of mainly three things. It's a PDF document, which as far as standards go, is a very easy read, and a header file, which defines all the functions that a model has to implement in order to comply with the standard. And some XML schema files describing a model description XML, which defines all the input and output variables that the FMU exposes. So the the header file, like the core functions of the header file, look something like this. I have removed some stuff from the original header file here to sort of reduce the visual noise. But basically, FMI defines these primitive data types that your variables can have. All variables are scalar variables, and so you have to implement these setters and getters for your variables. These functions are during sort of instantiating and initializing the model. And then you have this one function, FMI do step, which gets the input values, does the calculation and sets the output variables. And then you have some functions for teardown and cleanup after the simulation is done. The model description XML file looks something like this. This is an example of a very simple model. And sort of the most important part of this XML file for, in this case, is the model variables elements. It's just a list of scalar variable elements, which has attributes like name, variability, and causality, and some others as well, where the name is how a master algorithm would refer, or this is basically how we would identify the variable. And this is just an unrestricted string. It can be anything. The variability and causality are, so FMI defines a set of values that these attributes can have. And then contained within a scalar variable element, you have to select one of the data types which your variable has. And these has some other attributes, which is sort of relevant only for that specific data type that you have chosen. So if you would like to make an FMU by hand, you would have to first implement this C interface, compile it to a DLL if you're on Windows, and then package then make the model description XML file, which defines all the variables that your model exposes, and then package everything into a zip file, which has this structure. So this structure is also defined by FMI. So we have your zip file model.fmu containing the folders binaries, resources, sources, and documentation. These folders are optional, This one is required, and you must have at least one of these. These folders contain the binary files for that specific platform. And in this example, we only have this one model DLL, which must implement this FMI functions.h, because this is what the master algorithms, this is how they talk to the model. And the last part is the model description XML describing the variables. And when you have made an FMU, the model description is sort of locked in, so this can't change dynamically for a given FMU. So if we look at, we can look at, we now have a lot of tools supporting with various support for FMU export and FMI import. We see this list here on FMI's home pages of all the tools that support FMI to some degree. And I mean, this list is growing, and Open Modelica is one of them. And if you make a model in Open Modelica, it can look something like this. Here we have made a spring damper with some inputs and outputs. And exporting this to an FMU is as simple as just going to File, Export, click on the FMU. And then it's going to generate this file, ospmodel.fmu, which is just a zip file. So I have unpacked it here. Here we see the structure I just showed. And if we look at the model description, which has been automatically generated by Open Modelica, we see that even for this very simple model, there is a lot of stuff here. And if someone sent this model to you, you can see that there's no documentation here. So as a developer, and you want to use this model in a simulation, you have to go in, or you very often have to go in and read the model description files. And we can see here that it's going to be very difficult to figure out which variables to use and what all the variables actually mean. If we see here, one of the variables was called S1. So I guess we just have to search for it here. And we see, okay, we have the S1 variable here. It's an input, it's a real, and the unit is M. I mean, the unit here is also just a free unrestricted string. So it's probably meters, but we don't really know. And it's very difficult just based on this to know what the variable actually mean. And it's very limited what kind of validation we can do for connections that this variable is used in. It's basically just the causality and the data type that we can use for validation. Yeah, so now I'm going to go over to demonstrating how to make OSP model description files. Let me see here. So this is the system that we're looking at. It's the same that Håvard showed, just in a schematic form. So we have a mass FMU connected to a spring FMU and a damper FMU. And these moves around in the can move around in the XY plane. So we can imagine that we are a system integrator, and we receive the FMUs for each of these models from individual model developers or separate model developers. So these models are developed separately. And what we receive is a damper FMU, a mass FMU, and a spring FMU. And if they have not implemented an OSP model description, we would very quickly have to resort to the FMI model descriptions and have a look at what the input and output variables of each FMU are. in order to figure out how we can use these models and connect them together to run some simulations. So if we look at the damper model description first, we see that, okay, it has 2 inputs and 2 outputs. The names are, for us, rather confusing, but this is when you encounter FMUs in the wild, this is very often what you see. So in this case, these are the velocity inputs, and these are the damper force outputs. For this spring model description, it's the same thing. We have some parameters. We have some scalar inputs and outputs with some ambiguous names. In this case, these are the spring displacement, and these are the spring forces. For the mass, it's the same story. We have the input forces up top here, and we have sort of 2 sets of forces, and it looks like these 2 are one set of variables, and these 2 are another set of force inputs. And then we have some velocity outputs here and position outputs here. So one thing is that it's difficult to actually figure out what the variables really represent, but we see here that these 2 variables, they are actually connected somehow. I mean, you're supposed to use both of them together. You can't connect these 2 to the same thing. You have to connect these 2, and that information is not stored here. You have to find that somewhere else. So with if we after some trial and error, we're going to figure out that this is the correct way to connect all these variables. And I'll now show how to make first an OSP system structure XML file with the connections without using variable groups, so just using variable connections. So this is the OSP system structure XML. In order to save some time, I have predefined the simulators here. So the simulators are defines the simulators that we're going to use in the simulation, and a simulator is defined by a name, which is free to choose, and the source, which is the path to the FMU that this simulator is going to use, and kind of define a set of initial values. So okay, let's make some connections. So for a given OSP system structure XML, all the connections are defined inside of this connections element. We're not going to make variable group connection now, only variable connections. And one variable connection consists of 2 variables. So we want to connect, remember, this is the system that we're trying to define here in OSP system structure XML. So we have the mass simulator, and the variable name was out LU spring connected. So first I want to make these position connections over here. So that's one variable. The next one, W, YX. So now we have connected sort of this position set of variables here. The next I'll write this force connection. So the first one there was in LU for XX. and for yx. So as you can see, it's very easy here to make a mistake where we, for instance, make a typo like this. So in what we have done here then is that we have connected this output to, this output is not connected. This output is connected to both that input and that input. And this is an error that is very difficult to figure out. You basically just have to run simulations and try to interpret the results. But we would like to have some tool that is able to tell us that we have done something wrong here. The system that you have connected doesn't make sense. But if you're only using variable connections and the information in FMI model description XML, that's very difficult to do. So I'm not going to write out the variable connections between the mass and the damper as well. I've already prepared that here. So we can see now that even for this very simple system, we have all the 8 of these variable connections, and it's very difficult to make any sensible validation here. Okay, so let's, if we make the model developers make the OSP model description XML models for us, or OSP model description XML files for us, then we will have more information such that the connections will be easier, and it's easier to interpret what the models actually represent or what the interface looks like. So let's try now and make an OSP model description XML for the damper. So at the outermost level here, we have unit definitions and variable groups. So let's first make variable groups. And I'm using an IDE here that gives me all the variable group types that's defined in OSP-IS. But if you don't have that available, you can navigate to the XSD documentation for the OSP model description on the Open Simulation platform page. And here you have a list of all the variable group types that we have currently defined. And right now we see that this connection here between the damper and mass consists of a force and velocity pair. So this is actually what we call a linear mechanical port. And if we look in the documentation here, linear mechanical port type, we see that the linear mechanical port type consists of a force and a linear velocity variable group. And a force type contains 1 to 3 variables. So let's try to make one of those for the damper. Linear mechanical port. And yes, we have to give it a name. This is an unrestricted string, and the linear mechanical port variable group consists of a force variable group and a linear velocity variable group, which we also have to name. And in our case here, we have two force variables. In the damper model description, that was df0 and df1. df0, df1. And so the variable, so the whole point of this OSP model description XML file is to add a richer description of the model description XML file that's inside the FMU. So the variable element here with the ref attribute, this has to refer to a variable name that exists in the FMI model description XML. For the linear velocity, that was called LV0, LV1. Like so. And before I leave this one, I would like to also add some units to these variables. Before I do that, I have to make these unit definitions. It's the same way as the as in FMI2, a unit with a name, and a unit contains a base unit. And the base unit is a set of exponent values for SI, a set of SI base units. So for the Newton, we have kilogram, 1 is 2, and we can also add a factor and a offset. So here, in this case, the factor is 183. We'd also like to have a unit for the linear velocity. Let's make another one. Call that one meter per second. And in order to tag these variables with these given units, we just have to add the unit attribute here and specify the same value in this field as for the name of the unit. Like so. For the then we so this is what you do as a model developer, and the model developer knows what the units are supposed to be and what all the variables actually represent. So we can continue and do this for both mass FMU and spring FMU, but I have prepared that up here. So for the So this was what the OSP model description XML for the damper ended up looking like. We have a linear mechanical port with a force and linear velocity. The spring is very similar, but instead of a linear mechanical port, it has a linear mechanical quasi port, where the only difference to the one in the damper is that instead of a linear velocity, it's a linear displacement. And I should mention here that our restriction that is implemented in the ontology in the OSP interface specification is that for a linear mechanic or for any port, all the causalities of all the variables here must be opposite of the causality of all the variables here. So look at the mass. The mass OSP model description defines a linear mechanical port and a linear mechanical quasi port. So if we look at the connection diagram now, we see that, okay, so the damper has a linear mechanical port called mass connector, which can connect to the linear mechanical port defined on the mass. And likewise, the spring has a linear mechanical quasi port, which can connect to the spring connector on the mass. And in fact, when we have done this, we see that we have enough information here to actually infer that there is only one valid way to connect this system now. If you try to connect the linear mechanical quasi port on the spring to the linear mechanical port on the damper, you're going to get a validation error, and we will have a look at that shortly. So now that we have variable groups defined in OSP model description XML, let's try or let's see what the OSP system structure XML looks like for a system like this. So the simulator definitions are the same. The point of interest are here in the connections, and we see that instead of having all these individual variable connections, we have these two variable group connections, which we are also, in addition to reducing the number of connections, we also have increased the possibility to make sort of sensible validation on whether this system or configuration is correct or not. Yeah, so now I will try to run the OSP validator on this OSP system structure XML, and then I'm going to show what the validator is going to do when it's validating a configuration which has some issues. So let's see here. Okay, so as part of the OSP project, we implemented a Java library as a reference implementation to how a validator can be implemented or can support the OSP interface specification. And the OSP CLI YAR is a very lightweight command line interface tool using this validator. It should be mentioned that it's by no means production ready, but it's just a simple tool that can be nice to use to sort of get as an introduction and start playing around and getting familiar with OSP-IS. You can download it on from the GitHub pages for the Open Simulation platform in the OSP validator repository. It has a releases page, and currently I'm using this version. So if you download this one, OSP CLI YAR, you get one YAR file that contains all its dependencies. So first, if we just run it like this, we get a simple usage printout. It has two commands, one for validating OSP system structure and one for validating a single OSP model description, for which you also have to specify which FMU the OSP model description file is supposed to represent. Okay. So if we now run the validator on this one, we don't get any output because this is this particular OSP system structure is valid. It has no problems. It's connected correctly. However, let's see what happens if we actually have some problems with the configuration. So I have prepared two examples here. In the first one, the OSP system structure XML is the same. The connections themselves sort of appear valid here. But in the mass OSP model description, the linear velocity, or one of the variables in the linear velocity of the linear mechanical port, has accidentally used the wrong unit for one of its variables. So actually this connection or this system should then have some problems because this variable group is not valid. So let's try to run the validator on this system. Okay. So because of now we get some output, so it prints out one line for each validation error. My zoom settings here makes it a bit difficult to read, so I have prepared this printout in my IDE here, so it's a bit easier for us to look at. So immediately we see that here we have a list of validation errors. And we see that on line 15 and 20 in the mass OSP model description XML, we have some issues. And it says that first of all, it says that this particular variable group contains invalid nested variable groups. And on line 20, it says that the linear velocity variable group contains variables with incompatible units. So, okay, if we jump into the mass OSP model description XML, line 15, so the port is containing variable groups with some validation issues, and it was on line the variable group on line 20 contained variables with incompatible units, and we see that that is the case. So this is an example where using the validator and having a well-defined OSP model description XML is able to catch potential sneaky and difficult to find bugs before you run the simulation. The second error that I want to show you, and yeah, second and last one, is here I have fixed the issue in damper or in the OSP model description XMLs, so they are fine. But in the OSP system structure, I have removed the connection between the mass and the damper, or between the mass and the spring. So now I only have a connection between the mass and the damper. And since I've written this manually, I made a typo here, and I accidentally connected the spring connector on the mass to the damper. So what I'm doing here in essence is that I'm connecting a linear mechanical quasi port to a linear mechanical port, and that should not work. So let's try to run the validator on that one. Okay, again, we get some validation error outputs, and I've also prepared those here. Now we see that the first thing we can take note of is that the only place where we have problems is in the OSP system structure XML. So that's as expected. And we see that on line 37, it complains about this variable group connection. Because they have, and it's invalid because they have different types, namely a linear mechanical port and a linear mechanical quasi port. And it also goes a little bit further because a linear mechanical port and the linear mechanical quasi port has the force variable group in common, but the difference is in between the linear velocity and the linear displacement, which are two incompatible variable groups. Yeah, so that was all I wanted to show. So I just thank you for your attention and give the word over to Lars.
Thank you, Martin. I never thought I'd enjoy watching XML files being made, but I actually did. So thank you for that. We will now take a 10-minute break. So the seminar will continue at 10:25. So now everybody has the opportunity to stretch their legs a bit and be back here at 10:25 Norwegian time. So see you in 10 minutes.